Taylor polynomials and Taylor series are a topic that are found commonly in your higher level calculus or mathematics courses. They allow us to calculate things that would be normally pretty difficult, but by expanding a function into a polynomial, Taylor series and Taylor polynomials will actually allow us to get around the complexity of things by making it simpler by using a polynomial. So for instance, let's say I wanted to find the integral of e to the negative x squared dx. Well, looking at that, normally we would think about methods such as u substitution. However, that fails here because my u in this case would have to be negative x squared, and there's no du of that negative 2x in the original integrand. So instead, let's say I took this integrand of that e to the negative x squared, and I expand that out into a polynomial. It would look something like this. So expanding it out, e to the negative x squared is equivalent to 1 minus x squared plus x to the fourth over 2 factorial minus x to the 6th over 3 factorial. Dealing with this left side makes it very difficult to integrate if that is my integrand. However, once I expand it into this polynomial, this is actually really easy to integrate. I just go term by term with the anti-power rule. So the integral of this side, which is equivalent to e to the negative x squared, would look something like this. So then the antiderivative of e to the negative x squared would go to x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial. Of course, this just keeps going on into infinity, and then you have plus the constant at the end. That is just one example of why expanding something into a polynomial would make our work a lot easier. In terms of other real-life applications, Taylor polynomials are actually also used to approximate trigonometric, logarithmic, exponential values in the days before calculators were actually of common practice. So think about this for a moment. In your calculator, if you want to find sine of 0.2, all you do is just type in sine of 0.2. But 100 years ago, they couldn't do that because they didn't have an actual digital device that they could type it into. So instead, what they had to do was they had to expand it out with a Taylor polynomial, then plug in that 0.2 and actually get an approximation using what we call a Taylor polynomial. Now, before I actually get into what a Taylor polynomial looks like, I want to show you another example. So let's say that I'm dealing with the trig function sine of x, and I'm looking at it graphically. So this red wave is sine of x. I can approximate this trigonometric function by dealing with a very small degree Taylor polynomial, where I'm going to go to the 5th degree here. And by doing this, this is going to give me an approximation of sine of x around where it is centered. In this case, it's centered around 0. So if you look here close to the origin, the blue represents x minus x cubed over 6 plus x to the 5th over 120. That 6 came from 3 factorial, 120 came from 5 factorial. And if you look right around the origin, it matches perfectly with sine of x. Now, the further we get away from its center of 0, the further it deviates. You can tell it really deviates on the endpoints here. And so to alleviate that, what we could do is just increase the degree of the polynomial we are using to approximate sine of x. So instead of going to the 5th degree, let's say I went to the 20th degree. That means the blue curve and the red curve would actually converge to the same values further out, and they would follow the wave pattern of sine of x for a longer length of time, versus this 5th degree polynomial only starts converging here and then ends here, and then it starts to deviate and diverge off of what sine of x actually is. So the higher the degree of the Taylor polynomial we use to approximate a known function, such as sine of x, maybe e to the x, ln x, the closer the approximation actually is going to be. So now let's actually get into the definition of a Taylor polynomial. So we're talking about an nth degree, where n could be any number you choose. So if f, which is f of x, has n derivatives at x equals c, then the polynomial p sub n of x is equivalent to f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial, and this just keeps going till you get to whatever degree you want to define it at. So if you want to go to the 7th degree, then you would have f to the 7th derivative of c times x minus c to the 7th power over 7 factorial, etc. This entire thing expanded is called the nth degree Taylor polynomial for f of x centered at x equals c. And this is named after Brooke Taylor, an English mathematician who came up with this in the early 1700s. Now, if your center happens to be at x equals c, then it has another special name that just involves when it's centered at x equals c, and that is called the Maclaurin polynomial. This is named after Colin Maclaurin, who was a Scottish mathematician. So his is very similar to Taylor's polynomial. The only difference is you're centered at c. So then instead of having the formal definition with c actually typed in, you just replace all the c's with 0. So p sub n of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared. Notice on the Taylor polynomial it was x minus c quantity squared. Well, x minus 0 is just x squared over 2 factorial plus the third derivative at 0 times x cubed over 3 factorial. And of course this just keeps going until you get to whatever degree you want to estimate the function to be at. So let's look at a very basic example of this. It says, suppose that f is a function which has continuous derivatives, and that f of 2 is equal to 3, f prime of 2 is equal to negative 4, f double prime of 2 is equal to 7, and f triple prime of 2 is equal to negative 6. So we're looking at finding a Taylor polynomial of degree 3 for f centered at x equals 2. Well, first let me just go ahead and rewrite what the Taylor polynomial looks like. That way we have a basis for how to set it up. So the Taylor polynomial said you're going to start with p sub n of x is equal to f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus, and of course that just keeps going, but since I ran out of room I'm just going to stop there. So applying that to what I have here, we are finding p sub 3 of x, because we're looking for a third degree Taylor polynomial. F of c, well your c is equal to 2 in this case because that's my center here, and so f of 2 is equal to 3 plus f prime of 2 is negative 4, so I'm actually going to rewrite that part as minus 4 times x minus c, well that's x minus 2, and then plus f double prime of 2, which is 7, times x minus 2 squared over 2 factorial, and then plus f triple prime, which is negative 6, times x minus 2 cubed over 3 factorial. This is your third degree Taylor polynomial that is centered at 2. Now that one's pretty easy because they already gave you all the coefficients for the different derivatives to just plug in. But most of the time we actually have that given to us, and so when it's not given to us, we're going to have to actually write it out by actually calculating all the different derivatives and plugging in the center ourselves. So this is an example of that. It says, find the Taylor polynomial of degree n equals 4 for which f of x is equal to e to the 3x at 2. So my center is 2. My function that I'm trying to expand into a Taylor polynomial is e to the 3x. And so because I want a degree of 4, that means that my coefficients are going to have to go to the fourth derivative of f of x. So what I want to do first is go with my f of x and calculate all the way down to the fourth derivative of that. So I start off, I'm going to make kind of like a little table here. So f of x is equal to e to the 3x. I'm going to calculate f prime of x. Well, that's just going to be 3e to the 3x. F double prime of x is going to be 9e to the 3x. F triple prime of x is 27e to the 3x. And then the fourth derivative of your f is going to go to 81e to the 3x. Now, those are all my derivatives, but in order to get the coefficients for the Taylor polynomial expansion, I need to figure out, well, what are those values at the center, which in this case is 2. So on the side, I'm going to go back, and I'm actually going to plug in x equals 2. So then f of 2 is equal to e to the 6th. F prime of 2 is 3e to the 6th. F double prime of 2 is equal to 9e to the 6th. F triple prime of 2 is equal to 27e to the 6th. And then the fourth derivative at 2 would equal 81e to the 6th. So that part's a little tedious. There's no quicker way really of generating all those numbers. You're just going to have to crank them out, unfortunately. But once you do that, then you can go back and actually write out your Taylor polynomial. So I want a Taylor polynomial of the 4th degree, so this is P4 of x. And with the Taylor polynomial expansion, I start off with f of 2. Well, f of 2 is e to the 6th plus f prime of 2. Well, f prime of 2 is 3e to the 6th times x minus c, which is 2, so x minus 2. And then I'm going to have plus the second derivative, 9e to the 6th, times x minus 2 squared over 2 factorial. I'm going to run out of room here, so let me go ahead and adjust this a little bit. Then I need the third coefficient, which comes from the third derivative, so 27e to the 6th times x minus 2 cubed over 3 factorial. And I'm still running out of room. And then the last one, the fourth derivative coefficient, came from 81e to the 6th times x minus 2 to the 4th over 4 factorial. That is the 4th degree Taylor polynomial for f of x is equal to e to the 3x centered at x equals 2. Okay, so now let's look at one with the Maclaurin polynomial. So remember, the Maclaurin polynomial is just a Taylor polynomial. The only difference is it is centered at 0. So this one says, find the Maclaurin polynomial of degree n equals 5 for f of x is equal to sine of x. So if I need the degree of 5, that means I need to go down to the 5th derivative to find all the different coefficients before I actually build my polynomial. So this is the kind of tedious part where I'm going to have to actually just generate all the different numbers here. So I'm going to start by going through all the derivatives until I get to the 5th derivative. So my original function, f of x, is equal to sine of x. F prime is equal to cosine. F double prime is equal to negative sine. F triple prime is negative cosine. The fourth derivative is sine. And the fifth derivative is cosine. Now, I need to actually determine what are those values at the center, which the center for Maclaurin polynomial is 0. So if I go back and plug in 0, I have f of 0 is sine of 0, which is 0. F prime of 0 is cosine of 0, which is 1. F double prime of 0 is negative sine of 0, which is, again, 0. F triple prime of 0 is negative cosine of 0, which would be negative 1. The fourth derivative evaluated at 0 is sine of 0, which goes back to 0. And the fifth derivative evaluated at 0 is cosine of 0, which is equal to 1. So with your sine and cosines, you're always going to see a pattern where it's very cyclical, where it goes in a cycle, in a circle. Every 4 derivatives, of course, they just start repeating each other over in the cycle again, because that's how the derivatives of sine and cosine work. So now that I have everything, now I can actually build my Maclaurin polynomial. So the Maclaurin polynomial of degree 5 would be P5 of x. It starts off with f of 0. Well, f of 0 is 0, so I don't really have to write that, plus f prime of 0, which is 1, times x, minus, now f double prime, notice, is 0, so I'm not going to keep the f double prime. So then f triple prime is minus 1, and then it's x cubed over 3 factorial. The fourth derivative's coefficient is 0, so I don't have to put that in, because anything times 0 is just 0. And then the fifth derivative, its coefficient for the derivative is going to give me 1, and so I have plus 1x to the fifth over 5 factorial. So that's kind of the convenient thing about sine and cosine when you're dealing with Maclaurin polynomials, is half of the coefficients will actually end up being 0, so half of your terms cancel out, which is kind of nice. So your fifth degree polynomial, notice, only has 3 terms. So don't get the concept of terms versus degree confused. The degree refers to the biggest exponent. The amount of terms refers to how many actual terms you have being added or subtracted together. So that gives you a brief introduction to Taylor and Maclaurin polynomials. We'll look at more in another video that I'm going to post later on.